Hello my viewers, welcome once more to my physics lecture series. In this particular lecture series, I'll be looking at more examples of Newton's laws of motion. In my previous series, I talked about Newton's laws of motion, solved some examples, and so this is a continuation of the previous lecture series. Just want to look at more examples. We're starting with an Atwood machine. We have that. Let's assume that we have two objects. Those two objects, they have masses m1 and m2. Of course, we are given the condition that m1 is greater than m2. M1 is less than m2, and that they are connected by a light inextensible cord and hung over a frictionless pulley. Both the cord and the pulley, their masses are negligible. Now the question is, let us find the magnitude of the acceleration of the system and also the magnitude of the tension in the system. First and foremost, to tackle this problem, we are going to draw a simple diagram, a simple sketch to illustrate the information given. So we take our solution. So I can do this. Let this act as the pulley. So this is one of the masses. Let's call this one M1. And we have another mass, M2. So this is M2, this is M1. Now the tension is along the string. Since M1 is less than M2, it implies that M2 will be capable, since they are connected by a single spring or string, M2 is capable of pulling down M1. So the tension in M1 will be, let's call it T. The acceleration will be upward. So the acceleration at this point is directed upward. While in this case we have the tension is the same chord, but the acceleration in this case for mass 2 is moving downwards because M2 is pulling M1. So we have gotten a figure that we can work with. How do we proceed to find the acceleration and the tension? I can divide here into two. First and foremost, let's consider the forces acting on M1 and M2. We can use a free body diagram to illustrate this. Say, okay, this is for M1. This is M1. You have the tension acting upwards. This is W1. Then for the second mass, we have W2, which is M2 times G. This is M1 times G. And of course, the tension is also along the string, but the acceleration is acting downwards. this one is acting upward. So we have been able to represent this with a free body diagram. The next step to take is to look at the direction of the forces if we are pulling upward, because since M2 is greater than M1, it means we are pulling the rope or the string upwards. So if the string is going upwards, it implies that the tension in the string is greater than the weight of the object. That's why it is able to move upward. So we say that the total force, of course, we know that F is equal to ma from Newton's second law. So we can proceed now by saying, since the tension is along the string and we are pulling upwards, it implies that the tension is great enough to overcome the weight. So it's higher than the weight. So we say the total force will be the tension minus W1 is equal to M1A. We are using M1 because we are looking at mass M1. In this case, our tension will be equal to M1A minus W1. W1 is M1 times G, so our tension is M1A minus M1G. This is this is plus, because when it crosses the equality sign it becomes positive. So this is positive, positive. Now let's call this one equation 1, because we'll make reference to this equation later. So let's consider the case of mass 2. That's the second mass M2. Now we are pulling downwards because M2 is greater than M1. So because we are pulling downwards, it implies that the weight of M2 is greater than the tension in the string. So for M2, we'll say W2 minus the tension is equal to M2A. What is W2? M2G. So we say M2 times G minus tension is equal to M2A. And of course, we get expression for tension. The tension will now be equal to M2G minus M2A. Let's call this one equation 2. Since equations 1 and 2 are expressions for tension, we can simply say equate equations 1 and 2 so that is the case. M1A plus M1G is equal to M2G minus M2A. If that is the case, M1 is common on the left hand side of the equation, M2 is common on the right hand side of the equation. So we can factor out, say M1 into A plus G is equal to M2 into G minus A. But then we are looking for the acceleration. So we have to bring the masses, as in all terms that have acceleration, to one point. So if we rewrite this equation, we can say M1A plus M2A is equal to M2G minus M1G, since we are looking for A, acceleration. So we say A into m1 plus m2 is equal to g into m2 minus m1, so that our acceleration A is equal to m2 minus m1 bracket g divided by m1 plus m2. See how simple it is. So we can also calculate the tension using any of the expressions, either equation 1 or equation 2. So I choose to use equation 1, so that my T, I'll just simply substitute the expression for A into equation 1. So I say T is equal to m1 into A, which is m2 minus m1 all over m1 plus m2 g, which is this g, plus this m1g plus m1g. m1g is common to both sides, so we can factor out and say m1g into m2 minus m1 all over m1 plus m2 plus 1. If we further simplify, we'll have m1g into m2 minus m1 plus m1 plus m2 all divided by m1 plus m2. Minus m1 plus m1 is 0, so we are left with m2 plus m2, which is 2m2. So we have m1g into 2m2 all divided by m1 plus m2. So I can rewrite this tension T. Just permit me to, I don't want to use another page, so let me just put it here. So T is conveniently equal to 2m1 m2 into bracket of g divided by m1 plus m2. See how simple this problem is. Let's consider a second example where we are going to apply the knowledge we have gotten from this first example to solve problems involving Atwood machine. So we have a second example here. In an Atwood machine, one block has a mass of 3.20 kg and the other has a mass of 5.80 kg. The question now is we should calculate the magnitude of the block's acceleration and the tension in the cord. We'll just draw a simple diagram to illustrate the information and get a solution out of that. So how do we proceed? This is my Atwood machine. Okay. Let me use this circle to represent a pulley system. And this is the smaller block. and this is the larger block. So this is 3.20 kg and the other is 5.80 kg. Of course, we have seen that one is greater than the other. The tension is along the string and the acceleration of this block is directed upwards. Why is it upwards? Because this block is greater than this block. So this one has the strength to pull up this block. Then you have the tension in the string because it's the same string, but in this case the acceleration is downwards. This block is accelerating downwards. The first block is accelerating upwards. So the next thing is, how do we find the magnitude of the acceleration? We'll proceed like this. Since the tension in the string is directed upwards, because we are pulling upward, it implies that the weight of this block is less than the tension. Remember our free body diagram. Just draw a little free body diagram. Okay, this is the weight W1 equal to M1G. The tension is upwards. A is also up. This is tension. Then for M2, this is for the 3.20 kg. This other one, W2, is M2G. This is the 5.80 kg mass. Okay. This is the tension. Acceleration is directed downwards. So we apply our knowledge of forces. Since it is pulled upwards, the tension is greater than the weight. So we say that tension, recall that force is mass times acceleration. Then tension minus W1 is equal to M1A. That is for the first mass. So we say T, I'll have to split this into two. I want all the workings to be on one page. So I'll say that T, which is the tension, is M1A plus W1. What is M1? 3.20. Okay. So into A plus W1. Recall that W is mg. So M1 is 3.2. Our G has been taken to be 9.8 meter per second square. So while ignoring the units, we'll say 3.2A plus 31.36. This is the first equation for tension. Let's consider for M2. That's the 5.80 kg. Our equation there will be W2 minus T is equal to M2A. Why are we saying W minus T? Because it is being pulled downward, so the weight is greater than the tension. What is W2? M2G minus T equal to M2A. In that case, our tension T will be equal to M2G plus negative M2G minus M2A. So if we proceed, what's our M2 in this case? It is 5.80, so we say 5.80 into the bracket of 9.8 minus 5.80 times A. This gives us 5.8 times 9.8 gives us 56.84 minus 5.8A. Let's call this one equation 2. So since equations 1 and 2 are expressions for tension, we can equate them. So we say T1 is, well, we didn't segregate them as T1 or T2, but I've made the explanation. Since they are both expressions for tension, we equate them. So we say 3.2A is plus 31.36 is equal to 56.84 minus 5.8A. We take like terms to one side. We'll have that 3.2A plus 5.8A is equal to 56.84 minus, permit me to put it in another line, 31.36. So this gives us 9A is equal to 25.48. So our acceleration gives us 25.48 all over 9. So that acceleration equals 2.831 meter per second squared. To two decimal places, we can say A is equal to 2.83 meter per second squared. Now, having obtained the value for A, we can substitute A into either equation 1 or equation 2 to get the value for tension. So, me using equation 1, I say T is equal to 3.2 into 2 points. I use 2.831 anyway, plus this 31.36 plus 31.36, all in Newton. So if we do that, then our tension gives us 40.4192, which we approximate to 40.42 Newton. If you use that of T2, if you use equation 2, you're going to get the same value. Let's just try it. Using equation 2, we say T is equal to 56.84 minus 5.8 into 2.831. This gives us 56.84 minus 16.4198. This leaves us with 40, that's 40.4202. So tension is approximately equal to 40.42 Newton. So either equations will give you the same answer. You see how simple this is. Let's consider one more example. For this particular problem, we want to consider an object being dragged along an inclined plane. So we have that we should calculate the acceleration of an object of an 8 kilogram box along a frictionless plane inclined at an angle of 30 degrees to the horizontal if it is pulled up the plane by a rope, applying a force of magnitude T equal to 50 Newton. Let's take G as 9.8 meters per second square. First and foremost, we have to visualize the problem by drawing a sketch, a diagram to illustrate the information. Then we proceed to use the free body diagram. So if we are looking at an inclined plane, we just draw a plane piece to the horizontal. This is 30 degrees to the horizontal, and this is the box being pulled by a rope. So this could be the rope. So we want to find the acceleration of this block. The first thing to do, okay, after this we can just use a free body diagram to illustrate the above information, treating the box as a particle and indicating all the forces acting on the box. So we just use a dot to represent that particle. This is the plane. Of course, this is our horizontal. This is 30 degrees. The tension is along the string. So our T is here. That's the force. Then we have the weights. First and foremost, we have the normal. This is the normal force. The weight is acting downwards. So W is mg. We need to find a component of the force along the x-axis. Since the box is pulled upwards, then of course it will overcome whatever force acting in the opposite direction. So let's find that force acting in the opposite direction. So we can say that, as you can see, this is like a triangle. So here could be treated as 90 degrees. And the sum of the angles of a triangle is 180 degrees. So if you have here as 90, you have here as 30. 90 plus 30 is 120. So it implies here is 60 degrees. If there is 60 degrees and this part is 90, it implies here is 30 degrees. So this is 30 degrees. So I want to find the component of the force along this axis. I can just get a dotted line. So using this triangle, let me say this is O, A, B. So I can say using triangle OAB, OAB, this is theta. I want to find AB. I have OA. So I can use opposite and what? Hypotenuse. This is the longest side, so opposite hypotenuse. So I say sine theta is equal to opposite, which is AB, all over hypotenuse, which is OA. So that AB is equal to OA sine theta. So OB so AB is, this side AB is parallel to this force. So AB could be likened to be the force along the x-axis. OA is the weight, and weight is mg. So this is mg sine theta. M is 8 kg and g is 9.8. Theta is 30 degrees, so we say sine 30. So if you evaluate that, this will give you 39.2 Newton. So the total force along this plane will be, recall that force is always equal to MA. So whatever total force you are calculating, you must equate it to MA. So our total force, since the box is being pulled upwards with this tension, it implies that the tension is greater than this component of the force. So we say T minus F is equal to MA. What is T? 50 Newton. What did we calculate as Fx? 39.2 Newton. All equal to, the mass is 8. Acceleration is A. So 10.8 Newton is equal to 8 times A. So that A, which is acceleration, is 10.8 all over 8. That gives you acceleration of 1.35 meter per second square. So the acceleration of that block is 1.35 meter per second square. So I'm going to end this lecture series here. Thank you for your time. Just remember to hit the subscribe button, so for more information, whenever I upload new videos, you'll be able to follow up my channel. Please, you can make your comments at the comment section. If there are issues you want us to address regarding this video, just put your comments at the comment section and it will be attended to. The next lecture series will be on statics.